So as a little bit of a recap, we started out with metallic bonding. And perhaps you can just quickly tell the people at your table what's involved in metallic bonding. So, Paige, can you tell us what's involved in metallic bonding?
It's the bonding of two metals, and they have delocalized valence electrons.
And what else do they have? Because if I just have delocalized valence electrons, I haven't actually got a metal, have I?
Is it the crystal? No, that's the other one.
Phone a friend?
Yeah. You phoning me? Yeah.
This is our bonding model for metallic bonding. Here's the delocalized electrons that you mentioned. But that's not all that's involved in metallic bonding, is it? What else is there?
The positive charge.
On? Where's the positive charge come from?
Cations.
It's the metal cation. Yeah. So we can't, like an answer to a metallic bonding question is not just delocalized electrons, okay? Because if you say just delocalized electrons, that's what you're saying, okay? And that's not a metal, okay? That's just a bunch of electrons. And because they're all like charges, they would all repel and they wouldn't actually hang around together anyway. So they have to have their partner in crime. They have to have the cation. That's where they came from. Does that make sense? That the bonding is between the electrons and the cations. So this part here is the bonding. That's what's holding it together.
So again, we're back to yesterday where it doesn't just bond to one, it's just bonded to all of them.
Yeah, it's a negative charge and it's got positive charges around us and it doesn't care. It's an indiscriminate attractor. As long as it's an opposite charge, and that's why it can move. They can move through because their attraction to, if they're moving, then this sort of attraction here will weaken and the others will strengthen, and then it will move along to the next ones where the attraction, all because of proximity, the attraction will strengthen to the next one and weaken to the one that's left behind. Okay, so that's metallic bonding. What about ionic bonding then? Can I pick on you again? No? Okay. Caitlin. Oh, actually, have a chat amongst yourselves about ionic bonding first. Because that was really helpful, Paige.
loses the electron.
Okay, so Caitlin, can I ask you now?
Yeah.
It's the bonding between a metal and a non-metal. It has the ionic compounds have like a crystal lattice structure of positives and negatives.
Okay, so we've got metal plus non-metal. We've got a crystal lattice. And we've got alternating charge. Yeah? Yeah. And the bonding is between the opposite charges, isn't it? Yep. Okay. Very good. So that's covered our metallic bonding and our ionic bonding, which is frequently between a metal and a non-metal. Well, we're going to focus now on non-metals. Now, we already know that our non-metals can bond with metals in ionic bonding, but they can also bond with each other. And so if they're bonding with each other, for example, if we think about oxygen gas, that's two atoms of oxygen bonded together. Now, they don't bond ionically. In an ionic bond, we've got the giving away and the taking of an electron. But when non-metals bond with each other, they share electrons. And they have to do this because if we think about what's going on in the for our valence shell, if this is an oxygen atom, and I've just got the nucleus in there, and I'm not worried about inner electrons, it's just the nucleus, if you like, and the valence electrons. Oxygen has 6, doesn't it? And if it had to bond ionically, which it can do, it needs to take in 2 electrons. It can't really give away 6. So it can bond ionically with the metal that's willing to donate those electrons. But if it's going to bond to another oxygen, then the other oxygen also has a very strong attraction for its electrons. And so it's not going to donate electrons. And so it has 6 as well. And what happens is that as they come together, we end up sharing pairs of electrons. Now, I'll draw this as a better diagram over here. And the way we draw this, in fact, is with an electron dot diagram. And with an electron dot diagram, I'm just going to represent the element with its symbol, its elemental symbol, here. And I'm going to arrange the valence electrons around the element's name. So it's got 6 valence electrons. Electrons hang around in pairs. And it's bonding now to a second one, and so that we can tell the difference between their electrons, I'm going to make this one have dots. And hopefully there you can see that we have 2 pairs. Okay, so this is a pair. In your diagrams, don't draw circles around your bonds, okay? I'm just trying to highlight them, because we could also represent this in this way, which is almost a Lewis diagram, where each of the bonds is represented with a line. And that line tells us that there are 2 electrons involved in that particular bond. So we have a double bond here between oxygen atoms because we needed 2 pairs of electrons. if we look at something a little bit simpler, say with hydrogen, well, each hydrogen only has one electron. And so when hydrogen bonds to form hydrogen gas, it can only form the one bond, and that one bond is made up of a pair of electrons with one electron coming from each hydrogen atom. Okay, so I could also represent that in this manner. Now, with our nonmetals, they tend to have covalent bonding, which is sharing of electrons. We tend to classify them by what they can't do rather than what they can do, because they are very, very different. And what they cannot do is they cannot conduct. Heat or electricity. Now, what do we normally call substances that don't conduct heat or electricity? What's another word?
Insulators.
Yeah. So these are insulators. And they, we can also divide this out. We need to divide this into two sections because we have some quite different structures. We have covalent networks and molecules. Oops, molecules. All right, so they're all sharing electrons, and we're talking still about non-metals. But let's focus in on our molecules to start with. We've used this word molecules before, haven't we? And do we remember what molecules means? Perhaps have a little chat amongst yourselves. What is a molecule?
Two or more.
Montana, what do we think is a molecule?
That it's a discrete particle that so nothing else can add onto it. That made no sense.
Okay, let's go with discrete particle.
Surely is that the one that's made up of two or more?
Made of two or more atoms, yep. Do the atoms have to be the same or different? Oh, okay. So if the atoms are the same, what does that mean? If the atoms are the same,
It's an element.
it's an element. And if the atoms are different,
Compound?
now because these are discrete particles and they're made up, most of them are quite small, They tend to be gases or liquids at room temperature. We've already said they're non-conductors. They can also be soft solids. And an example of a soft solid would be something like paraffin or candle wax. You know, that's a soft solid. It's not really hard. So, say, now, we can't really categorise them on the basis of solubility, but quite a lot of them are insoluble. So especially if we're thinking about our oils and waxes and things like that, they're not soluble at all. Yeah. But the main thing is for covalent molecular bonding, the bonding is covalent, and this is the structure. It's a molecular structure. Okay, so the bonding in a covalent network is exactly the same as the bonding in a covalent molecule because it involves the sharing of electrons. But the difference is that this has a molecular structure and this has a network structure. Okay, and we'll go on to talk about what that means in a moment. Now, talked about sharing the electrons, and if we turn over the page, you can see there's a bit of a diagram showing again that electron pair. The sharing of that pair of electrons representing one bond, and you can also see that there is the Electron Dot Diagram for fluorine, and this one here being the structural formula representation where you draw a line to represent a bond. And what we are trying to achieve in our bonding, with all bonding, is noble gas configuration. We're trying to achieve stability. So what we're looking for to do that is what? What do we need for that noble gas stability?
A full outer electron shell.
Yeah. And so for hydrogen, how many electrons is that? 2. But once we get bigger than hydrogen, how many is it? 8. Yeah. All right. So we talked also a bit about multiple covalent bonds. Now, how do we go about figuring it out? Now, I'll just do a couple more examples, and then I'm going to get you working on some electron dot diagrams. What about nitrogen? Whereabouts is nitrogen on the periodic table? Which group is it in?
15?
Yeah, it's group 15. What does that mean as far as how many valence electrons it has? 5. Okay, so the number on the end there is going to be the number of valence electrons it has. So nitrogen has 5 valence electrons. So it's got 1 pair, and it's got these other 3 valence electrons that are ready to bond. So if I have another nitrogen, what do you think it's going to do in order to gain noble gas stability or get those 8 electrons?
Does it share all 3 between the 2?
Yeah, it's going to share all 3. And so this one will have its unbonded electron pair out off to the side. Its other 3 valence electrons are then involved in forming a triple bond with another nitrogen. And if we look to see, well, and again, I don't want you doing this on your answers. You can do it to illustrate your thinking. But this nitrogen has access to 8 electrons. When we include the 3 from the other nitrogen, and the same the other way. Because remember, what we're after is those 8 electrons. And that's why this is very stable. Okay, so remember, I could also write it this way, representing the triple bond. But what do I need to do when I'm doing my electron dot diagrams, or when I'm trying to figure out the bonding? The first thing is I have